Hello everyone and welcome to this course on online aquatic geochemistry. In the previous lecture we have been discussing the application of particular isotope systems. We discussed the carbon and the nitrogen isotopes, and in today's lecture we are going to discuss some other isotope systems which are more of the non-traditional type, which are more these particular isotopes. We are still doing a lot of research and there are still a lot of things that are still unconstrained, specifically given the different kinds of hydrogeochemical settings, different kinds of climatic settings. Slowly people are doing more and more, data sets are coming up and there are more research being done. It is basically therefore an evolving subjects, and therefore you will find the lack of certainty that we saw with respect to oxygen isotopes, stable water isotopes and even carbon isotopes, okay, because those we have been doing for several decades and the understandings are pretty strong as compared to these few traditional isotopes which have much larger interactions in the natural system, therefore is very complex. And understanding these kind of complex behavior and to say something like to draw empirical conclusions from such isotope becomes very difficult. But what we know is that how a particular system behaves, okay, how a particular system is supposed to behave. It may behave differently in different hydroclimatic settings, but we have a certain expectation, okay, some background physiochemical hypothesis based on which we know that this is how this particular isotope system is expected to behave. Whether it behaves or not, we need to see the data. If it does behave, very good, well and fine. If it does not, then we need to see why it does not, what changes are happening that we are seeing a different scene that what we were expecting. So let's again I will show you this particular slide, and we are going to talk today about few isotopes. For instance, we are going to talk about boron, we are going to talk about calcium here, we are going to talk about iron here, we are going to talk about lead today, we are going to talk about lithium today, okay. So as you can see, they fill up different boxes. So one particular is so lithium, calcium, more of the weathering weathering signature. Boron, lead, again they have higher anthropogenic signature as well as geogenic controls. Iron is very redox sensitive and it's very complex in the natural system, and due to its high biotic interaction, its understanding is still in the process of we are still stumbling upon new discoveries as the studies are progressing. So let's first see this particular boron isotopes, okay. Now as I just mentioned in this previous slide, each and every system behaves differently, their applications are very different, and for particular for certain elements we are just trying to see how they behave, okay, and I will show you that using calcium isotopes. So that is for the progress of science, like how we are going to understand this particular isotope system. So for that we do not have a lot of background understanding, we are just going to investigate that particular isotope system in different kinds of samples, okay. Same thing for boron also, because boron also is an isotope that has can have many kinds of applications, but we need a lot of samples that to be analyzed, and there are not a huge many labs around the world that does boron isotopes, okay. So certain things we do, certain studies we do that shows how particular element is used in different kinds of settings, aquatic settings and all, while for some we have definite answers. For instance, the lead isotope system, it is very well understood. Okay. The behavior is very it is very straightforward in a complex system as well. It is straightforward in even in a complex system. Okay. So, that is why working with lead isotopes, trying to understand aquatic systems, sources, anthropogenic versus geogenic contributions to aquatic systems is much easily done with lead isotopes as compared to something like calcium isotopes. Okay. So, these kind of behavior is there as like element to element difference. So, if we look into this particular isotope system, the boron isotopes. So, boron has a valency of +3 and it generally binds with oxygen or hydroxyl groups, and there are two particular forms that we have. One is the trigonal form, that is the boric acid, or we have the tetrahedral form, that is the borate ion. So, this is how boron exists in all aquatic systems. So, in all aquatic systems, boron will either exist as either boric acid or borate ion, depending on the form, that is either it will be a trigonal form and it will be a tetragonal form. Now, what controls this? Okay. This control of boric acid or borate ion is formed by its pH differences. Okay. So, pH basically controls the formation of either boric acid or borate ion. Okay. So, at a lower pH, okay. Well, now let us see what is the equation first of all between boric acid. So, boric acid will interact with more water and it will form the borate ion and H plus. So, what is happening is at lower pH this boric acid dominates, okay, at lower pH, whereas in more alkaline conditions borate ion dominates in the aquatic system. So, in the more alkaline natural setup, so say suppose in seawater that ranges between somewhere and is close to around 8, we generally have boron in the form of borate ion. Okay. So, it is the borate ion that is prevalent in seawater given the present day pH conditions, that is close to 8.1. But if it changes to more acidic form, then it changes to BO boric acid. Okay. It changes from borate to boric acid with more and more acidity. Now, not only just these two forms are different and their controls are different, their isotopes also get fractionated between these two forms. Okay. So, 10 boron prefers this, 10 boron prefers the borate ion, while 11 boron, the other isotope, prefers the boric acid. Okay. So, boric acid is enriched in 11 boron, while the borate ion prefers the 10 boron. Okay. And these kind of variations arises due to the difference in the bond strength and the vibrational frequencies of the trigonal form and the tetrahedral forms. Such differences occur leads to the isotopic fractionation, okay, and therefore 11 boron is preferred in the more trigonal boric acid, while the 10 boron is more preferred in the tetrahedral form. Now, what is that particular this use? This particular information we have been using to understand the pH variation in Earth's seawater over its historical time. Because of its pH sensitivity, because of its pH dependence, and this and this preference of particular isotopes to particular forms, we have been able to use this delta 11 boron, that is the boron isotope value, okay, this delta 11 boron value to identify how the pH has changed over Earth's history. Where are we measuring boron from? What is there in, what are we doing? So, boron is easily incorporated in carbonates as impurities. It is just that this the borate ion, okay, the borate ion, it just replaces the carbonate ion in the shells of microorganisms, okay, like foraminifera, different kinds of foraminifera. What happens then is, when we test this particular species of forams for its delta 11 boron composition, the delta 11 boron of the carbonate is equal to the delta 11 boron of the seawater. Therefore, these carbonate delta 11 boron is a direct recorder of the ambient seawater pH, because pH controls the borate ion availability, the borate ion availability. So, whether if it is low value, whether it is high value, we are going to see. How are we going to see? Okay. What happens is, when seawater pH increases, that means it is moving towards more alkaline formation. More and more boric acid gets converted to borate ion, right. More and more boric acid gets converted to borate ion. What happens then? The 11 boron, which was originally there in the boric acid, now has to find its place in the borate ion. Okay. So, this borate ion gradually gets more and more 11B enriched. So, the delta 11B moves towards more enriched and more positive values as the pH increases. As the pH is going to increase, 11 boron by 10 boron ratio increases, and the delta 11 boron value increases, therefore, in that particular high pH condition. And just the opposite happens in the opposite case, where if the pH is changing, if the pH is moving towards more acidic values, if it is moving towards more lower pH, then more and more borate ion is going to form more boric acid. So, the 11 boron preferring the boric acid phase is going to get depleted from the borate ion. Okay. So, the borate ion will lose its 11 boron to the boric acid. So, the delta 11 boron will decrease when pH decreases. Okay. Now, carbonates only take the borate ion, they do not take boric acid, they cannot use a boric acid in their structure, they will only prefer the borate ion. Now, since the borate ion has lower 11 boron by 10 boron ratio, therefore, the delta 11 boron of that particular carbonate is also going to be low during this low pH conditions. Therefore, we have a direct relationship between the delta 11 boron of carbonate, the delta 11 boron of the seawater borate, and the pH. Because remember, these carbonates, they are getting precipitated at equilibrium. So, therefore, this delta 11 boron of carbonate is equal to the delta 11 boron of seawater. Now, sometimes there is a correction required, there can be a difference, there can be a fractionation between the borate of carbonate and the borate of the seawater. It can vary by few parts per mil, it can vary between few parts per mil, okay. But that variation is constant, that means that error can be applied, there is an empirical relationship that we can use to correct that data for this fractionation between water and carbonate. So, this using this relationship between borate ion and the pH, we have been able to determine what was the pH in Earth's past history. In fact, it is one of the very well recorded pH recorder. Okay. And you can see in this particular graph where we have seawater pH in the top axis, and we have atmospheric carbon dioxide, and you can see how with increasing so this is age. So, this is atmospheric carbon dioxide in ppm, and we are going to see how in the past atmospheric carbon dioxide has changed, whether this particular change is reflected in the seawater pH condition as well. And we do observe very high variations in change in the atmospheric carbon dioxide concentration during the Eocene phase. Okay. And corresponding to that, we observe the high variations in pH as well. And in today's world, we can see that there is a rising carbon dioxide concentration and lowering of pH trends as well. Okay. So, this kind of record, boron isotopes, has got wide applications and has been used widely. Okay. Moving to the next, so this is boron isotopes in applications in the terrestrial ecosystem. So, that was boron isotope application in marine ecosystem. Now, look at the terrestrial ecosystem application. So, this is a plot showing the delta 11 variation in the y axis, and in the x axis we have the concentration of boron. Okay. We have just the concentration of boron. And the reason you can see we have such wide application of boron is how it can well separate different different end members. For instance, you see this is coastal area. So, coastal area, the isotope composition is very narrow and it is very distinct. Similarly, the anthropogenic contribution is also very distinct. So, such distinct source signatures helps us understand what is the proportion of mixing. So, here you see the other mixing between the coastal rainwater and the continental rainwater with the anthropogenic contamination coming in. So, the coastal rainwater, when it mixes with the anthropogenic contribution, it has this kind of variation. It has this kind of variation showing the mixing of the anthropogenic pollution with the natural coastal rainwaters, that is forming the signatures in the continental rainwaters. So, this kind of source specific signatures, isotopic signatures, becomes very helpful. And not only boron has source specific signatures related to continental, it also is extremely reactive in terms of biotic interactions. Okay. Plants, animals, all of us, we have boron in our system. Boron is specifically very important for plants for its metabolic activities, and therefore, it is uptaken and it is released during the plants processes, the metabolic processes. So, when we are looking into critical zones, from the critical zones we have got data to show how boron composition varies between different components. For example, here you have the Mulehole CZO data, which is the Kabini river is a sub basin of the Kaveri river. Okay. So, this is from the Kabini watershed. Okay. So, this particular CZO is a small critical zone observatory that we have near this place called Mulehole, and as you can see that there is the data for different types of samples. So, there is soil, there is the gneissic rock, that is the bedrock, then we have litter, we have plant litter, that means leaf litter. Okay. So, this is leaf litter, dead leaves. Then you have groundwater data, you have stream water data, you have soil seepage, that means the first few centimeters into the soil, then you take some of the soil water, you try to extract some of that soil water and you find the soil seepage. Then there is overland flow. Overland flow means something that is not seeping inside, it is just flowing as a sheet on top of the soil. So, that is overland flow. When the soil is absolutely saturated, there is no seepage going on, and if it is going on, it is in a very slow process. So, there is a overland flow that is happening. Okay. So, that process is there. Then there is the actual rainfall, and then we have something which is called through fall. What is through fall? Through fall is when the rain hits, but this rainfall mixes with the plant exudates. So, it is falling on the leaf and then it is falling on the ground. So, this is called through fall, that means it is mixing with the dust, it is mixing with the plant exudates that is there on the leaf surface. So, leaf surfaces also accumulate a lot of dust and also is giving out a lot of excretes a lot of exudates. So, these are called plant exudates. So, when the water mixes with this dust and exudates, it has a different signature. So, that is called through fall. So, the original rainfall can shift its signature. Okay. Similarly, this is the data from another critical zone observatory in Strengbach, which is in Germany. Okay. And here also you can see the through fall data, the rain, the soil seepage data, soil solution, a stream, groundwater, vegetation, but rock is absolutely different. So, by having such kind of differences, when we are looking into an entire system functioning, for instance, you want to see how boron is getting cycled inside the critical zone. So, you need to know, okay, so this is my bedrock has this value, then from the bedrock this is my soil that is formed. So, the soil is of this particular value, but when I am moving it into soil solution, the value is this, the plants are uptaking this, okay, and the through the through fall, it is returning back whatever the plants are uptaking, it is returning back through fall again onto the surface of the soil. Okay. So, this soil solution not only has rainfall, it also has this through fall, that is the return back of the vegetation incorporation that has happened. And finally, the soil solution, the springs and the groundwater, they can all contribute to the stream. Okay. So, if you want to know how this particular system is cycling elements, boron is a very good tracer of that, because it is coming from weathering also, it is coming from biotic interactions also, okay, and it is also coming from distance seawater. Okay. So, seawater also has very specific isotopic composition. So, coastal areas will have different values, continental areas will have different values. So, the rainfall itself will have different values in different regions. Okay. So, we have differences in soil and rocks, we have differences coming from the ocean water mass itself, and we have the biota to cause the differences. Okay. So, all this kind of differentiation and fractionation with the different kinds of set of samples, for instance the through fall, the litter, soil. So, such compartments in the critical zone, we can easily identify and quantify how the elements are getting cycled. So, this was the application of boron isotopes in the critical zone, and of course, aquatic systems, they are going to follow this kind of cycling, and they are going to help in this elemental cycling in the critical zone. So, that is why whenever we look into aquatic systems, it is not only the aquatic system that we look now, we try to figure out how it is behaving in the critical zone itself. So, as I said in the first 2 lectures, that slowly we are moving from understanding of one particular system to looking into the entire critical zone. Moving on to another isotope system, which is lithium. Lithium again is a very different element. It is extremely specific to weathering, okay, because it does not it is not an element that gets involved with organic interactions. There is no biologically mediated reactions wherein lithium takes part. It is very specific to weathering. Okay. It has 2 isotopes, 6 lithium and 7 lithium, and this means that there is a 15 parts per mil mass difference. It means 1 by 6. Okay. So, 1 by 6, that means 7 minus 6 is the difference in the mass of the 2 isotopes is just 1, and divided by the major isotope, the major abundant isotope, which is 6. So, that is the 15% relative mass difference, and which is one of the largest for all the metals except for calcium. And lithium is an excellent tracer of water rock interactions, not only at different lithologies, but for also lithologies that can be separated by different geologic climatic settings and weathering activities. And by weathering activities, I mean not only static or steady state equilibrium weathering, but also dynamic weathering. Okay. And we are going to see how this is explained. Also important to note is that lithium now is an element which is not only having a lot of weathering supply, but we have also started using, as humans, we have found lithium to be useful in particular applications. So, its application has now increased in the commercial products, such as in different kinds of chemicals and drugs and fertilizers, and in different kinds of lithium batteries and all that. So, although in most of the settings you expect lithium to be of geogenic origin and very specific of weathering activities, but with its proximity to anthropogenic anthropogenic hotspots. For instance, if you have suddenly an area where there is a lot of population, industrial population, then you should be careful whether that particular aquatic system lithium is coming from natural sources only, or there is some supply from anthropogenic contributions as well. Okay. But that again is very specific to places which is close to anthropogenic hotspots, such as industrial regions or large cities, things like that. Okay. Let us look into the lithium isotope variability. So, as you can see here, there is a huge variability in the different types of samples that we can see. Okay. And it is very specific. Now, lithium isotope is very specific because it is strong fractionation between the minerals and the water. Okay. And here you can see why. So, the light isotope of lithium, that is 6 lithium, prefers the mineral phases. Okay. So, it likes to stay in the clay, it likes to stay in the minerals itself. Okay. And the heavier isotope, the 7 lithium, is therefore partitioned into the water. So, when there is a primary weathering happening, the original mineral weathers to form a secondary mineral, and often at times it is some kind of clay mineral. So, during this interaction, the 6 lithium is partitioned into the clay mineral. It likes that clay mineral. Okay. So, it is partitioned into that clay mineral lattice. Whereas, the 7 lithium heavier isotope, that is released into the water. So, my water will have a heavier or a more positive or enriched 7 lithium isotope composition. Whereas the minerals, the rocks and specifically the secondary minerals, they will have a lower delta 7 lithium isotopic composition. So, here you can see that the suspended load in rivers, they have a lower 7 lithium isotope composition as compared to the dissolved load. The dissolved load is way positive. So, this is a very important distinction between the dissolved load and the suspended load. The sea water has a very unique value. Okay. The crust, again the crust has different values depending on the weathering and the activities that is going on in the region. So, this is the values in the mantle and the morb region, and again these are meteorites and extraterrestrial. So, beyond the earth, this is the value, whereas in lakes, as you can see, again just like rivers, the value is more positive. This is brine, this is groundwater, this is submarine hydrothermal water. So, such variations help us understand what kind of processes is going on. For instance, let us look into this particular figure where we have this del 7/6 lithium. So, this difference is between the isotopic composition difference in the suspended load and the dissolved load. So, what is the difference between the suspended load and the dissolved load plotted against the dissolved load data? And it shows that with higher dissolved load, more heavier dissolved load data, the differences are more and more negative. And that is, of course, that is because this 7 lithium is now partitioned into the water. So, its value in the water will be much heavier, and therefore, this suspended load and the dissolved load will be more and more negative. So, therefore, the inverse correlation. Now, if we separate out the suspended load and the dissolved load in separate axes, you can see here the plot again. And this plot, you can also see the differences between the lithologies. For instance, a square, which is the carbonate, is absolutely different within the ellipse, it lies within the ellipse as compared to the triangles. Okay. So, this is the carbonates and this is the silicates, and even in the carbonates there is a distinction with respect to altitude. So, this is carbonates in high altitude and this is carbonates in low altitudes, whereas such distinction is not present in terms of silicate rocks. So, this shows the usability, the applicability of lithium isotopes in understanding different source rocks such as silicate weathering and carbonate weathering. And for carbonate weathering, we can use it a step ahead to see whether it is a high altitude or a low altitude lithology. So, that is what I mean when I say that different kinds of isotope systems has different kinds of applications in aquatic geochemistry. Okay. Now, with this I will stop today and we will discuss more about applications of metal isotopes in our next lecture. Thank you.